let's do another example. So we got a pendulum problem here. Example 7.82. Now a good thing to do in your notes is to write pendulum problem and put a big star next to it. The reason you're going to want to do this is if you need to look back to figure out how to solve pendulum problems, you'll remember, hey, I put a big star next to it in my notes, and there it is. The difficulty with doing a pendulum problem simply comes from finding the height difference between the bottom of the pendulum and the top of the pendulum. That's why you might need to look back. All right, so let's go ahead and read this and get started. A small rock, all right, with a mass of 0.12 kilograms is fastened to a massless string. This sounds great. With a length of 0.8 meters to form a pendulum. The pendulum is swinging so that it makes a maximum angle of 45 degrees with the vertical. Air resistance is negligible. What is the speed of the rock when the string passes through the vertical position? And what is the tension in the string when it makes an angle of 45 degrees with the vertical? And what is the tension in the string when it passes through the vertical? Okay, so we got a little bit of review stuff in there too. But the first thing I want to find is I want to find out how fast is it going here at the bottom. So in that scenario, I have 0.1 here and 0.2 here. And I want to go ahead and solve for the speed at my 0.2. So let's go ahead and set up the work kinetic energy theorem as I go from one point to another. So there's no work in, no one's pushing this. Okay. There's no friction because air resistance is negligible. It is moving at 0.2. It's not moving at its maximum displacement. It comes to a momentary stop before coming back. The potential energy at the bottom. So I'm going to choose this point down here to be my height 0. And so then I just need to figure out what is this height here of that first point above it. Now it does say small rock, so I really should be considering it to just be little point dots. I drew it a little larger though. And then, so that one's 0, but it does have potential energy at 0.1. Okay, so this sets up pretty quick, and there is no elastic potential energy. So I have 0 is equal to K2 minus UG1. So I have MGH, we'll move this over to this side, substitute in our MGH, and kinetic energy 1/2 mv squared. So, oh goodness, the mass of the rock cancels out. Don't need to know it. Probably will for that review stuff though. So then I get V is equal to the square root of 2GH. Oh, well, that went pretty quick. The thing here is they don't tell us the height. They tell us that the length of the pendulum is 0.8 meters and the angle of the pendulum is 45 degrees. What they don't tell us is the height. So we have to go ahead and figure that height out. So this is what we have to do in this scenario. We're going to go ahead and find this leg of the triangle here. So this leg here is going to be L cosine of 45. What I can do now is I can say, okay, that's L cosine of 45. This whole thing is the length. So that means that my height is going to be the length minus that green part, L cosine of theta. So my height in this case is L times 1 minus the cosine of theta. This is the little star stuff you need for solving a pendulum problem. You need to be able to get from this picture to that height. So let's plug in that information we have. So we have the square root of 2 times 9.8 times 0.8 times 1 minus the cosine of 45. Complete that square root there. And when we type that in our calculator, we should get a number of 2.14 meters per second for that speed. Okay. So now for part B, they want us to find the tension at this point over here. Okay. So let's go ahead and draw ourselves a free body diagram here. So I have tension and I have gravity, mg. And I'll note that this angle is 45 degrees. Okay. So I want to find the tension. So that means this gravity, there's going to be a portion of the gravity, mg, cosine 45 pointing this way, mg sine 45 pointing this way. So if I think back to summing up the forces parallel to the radius. That's what we're doing here. We're going to figure out how much is pulling along that radial direction and how much is tangential. So this tangential part is going to cause it to accelerate, where this mg cosine 45 part is going to be what the tension has to support. So in our scenario here, the sum of the forces parallel to the radius equaling MAC. But when it reaches the top, what was the speed? It was 0. So this AC term is 0. All right, so now I have just tension minus mg cosine 45 equals 0. So I have the tension is equal to mg. So the m was, I think, 0.12 times 9.8 times the cosine of 45. Type that in your calculator. You should get something like 0.83 newtons. Now, as it comes down here, tension's going to be supporting more and more of the weight until it gets to this point. And so at this point, it's supporting all of that weight, but also it has to cause an angular acceleration, or a radial acceleration inward there. All right, so let's set that up. So now when I add up those forces parallel to the radius, set it equal to MAC, our AC is going to be our V squared over R in this case. So that V is going to be important that we had earlier. So now I have tension minus mg equals m times v squared over r. Now, just a important reminder, it wouldn't have mattered on this one had you messed it up, but remember, when we do this, we like to draw that direction of AC and always label it as positive. I'm sorry, this diagram's getting pretty messy here, but we always want radially inward as our positive direction of AC, because AC always points radially inward, and I'm labeling it as a positive value here. So go ahead, solve for tension. So I get my 0.12 times 9.8 plus 0.12 times v squared. So that was my 2.14 squared, all divided by my radius. And the radius is going to be equal to the L value, which was 0.8 for us. And so we should end up with a tension greater than our 0.83. So when we type that in a calculator, you end up with, I never calculated it. Son of a gun. Here, let's calculate it quick. Just like that, 1.86. 1.86 newtons. Calculator's fast. All right, 1.86 newtons. So yes, that is more than my 0.83. And there's your example.